So there you go. So I hope the method to find the QR decomposition is somewhat clear from what we did today. All you do is you take the columns of the matrix, right? You orthonormalize them. That allows you to build the Q, and then you simply take the transpose of that Q times A, and it gives you the R matrix. That's how to find the QR decomposition. There are also formulas in terms of dot products of the columns. You can build a formula for R from dot products of the columns of A with the vectors forming Q. Like I think if we, well, anyway, this is a good method. We don't need to have another formula to remember or think about. It's fine. All right. So, any questions?
Could we have just stopped at this problem and have it still work with Q? Because you wrote orthogonal, not orthonormal with Q.
That's the thing is an orthogonal matrix has orthonormal columns. So the language is not entirely in parallel. Be careful about this. We don't have a name for a matrix that has orthogonal columns. That's not a thing, as far as I know. Like I don't have a name for it. I do have a name for the matrix that R transpose R is equal to the identity. That's an orthogonal matrix. Admittedly, from the perspective of students not wanting to be confused, because of, like us mathematicians, we have this habit of naming things so that they're exactly what they sound like, right? Right until we don't. And so yeah, it would be nice if we called it an orthonormal matrix, right? But that's just not what we do, unfortunately. But that's a very good question. Like that is a perennial confusion among students, and with good reason. And I think I just figured out the reason I get confused about this topic. It's because the Q and the R, I think of R, for me, R is an orthogonal matrix. But that's not the case in the QR decomposition. The Q is the orthogonal matrix. Bah! Anyway, not my notation. But it is a standard notation, so I can't change it. All right? Okay, so let's talk for just a second here about normal equations. So suppose you're looking at A transpose A equals to B, right? Let's talk about normal equations and the QR decomp, right? Does the QR decomposition bring anything new to the study of normal equations? Like, is it helpful? Well, check it out. If A is QR, right, we've got QR transpose times QR, right, equals to B. But we know sock shoes, right? So this becomes what? This becomes R transpose Q transpose Q. Ooh. Hey, look at that. That's the identity, because Q is orthogonal. So the normal equations just read R transpose R equals to B. And so those are actually nicer than the normal equations, because you know the product of R and R transpose, it's not bad. I mean, you could you can play around with that. It's easier to solve than the original normal equations. So that's just a comment. All right. Let me go on here. So our next theorem is the real spectral theorem. And this is a big one. I don't prove this in here. I do try to prove this in 321. Sometimes I succeed, sometimes only partly. Okay, I don't usually, there's something in this that's technical, and I never quite prove it in 321 either. And it's a source of great shame to me. All right, because I feel like I should prove things. But the real spectral theorem for a matrix, all right, it says the following. If, oh, by the way, I did the QR decomposition for a square matrix, but you guys should see that this QR decomposition will still make sense for like a rectangular matrix. To make the QR question friendly on the test, I would just give you like a matrix with 2 columns. Because then the Gram-Schmidt of 2 columns is like very easy, right? Listen, the next surprise attack mission that I have not yet written, I will put one of those on there so you can have a chance to run through it, all right? Okay, anyway, so real spectral theorem. If A is a n by n real matrix, then, and A transpose is equal to A, then A is orthonormally diagonalizable, and all the eigenvalues, just to drive the point home here, are real. Orthonormally diagonalizable. So to put a finer point on this, what I'm saying is there exists, that is, there exists beta v1 through vn with vi dot vj equals to the Kronecker delta ij, and if we calculate beta inverse times A times beta, we simply get a diagonal matrix with the eigenvalues down the diagonal like this. So it's not just that it's diagonalizable. It's diagonalizable in the nicest possible way. So to make that even easier, take that inverse and make it a what? Like to fully appreciate the weight of this theorem, I'm talking about an orthonormal basis, so I shouldn't write beta inverse. What should I do? What have we learned? We don't inverse. We what? Transpose. And that's like much, much easier. So this is how we diagonalize if the matrix and symmetric is a simple condition to check, right? Man, that's nice. All right, so let me see if I can show you guys an example, if I have one. Probably we can do it like a 2 by 2, right? So we'll be talking about this real spectral theorem for about the next hour of class, probably. Like, there's tons of applications of it. It's not just this. Like, the things we can do with this, very, very nice. Very nice. Okay, so here's a matrix. A is, I don't know, let's say 1, 2, 2, 1. That's a nice symmetric matrix, I think. Right? What are the eigenvalues of this thing? I've got lambda minus 1 squared minus 2 squared. That factors to lambda minus 3 times lambda, plus 1, I think. Am I right? We'll find out soon. If I'm right, when I look at A minus 3i, right, times u1 what's that going to give me? Minus 2, 2, 2, minus 2, UV, right? Haha! Look at that. So U1 is equal to, looks like 1, 1, right? Lambda 2 equal to minus 1, I'm claiming. So I should look at A plus I times U2. And that is 2, 2, 2, and 2. So obviously, quite manifestly, we have the same equation on repeat, and we get U2 is equal to 1 minus 1. You can check me, right? 1, 1, when you multiply it by the matrix A minus 3I, we get 0. And 1 minus 1, when we multiply it by the matrix 2, 2, 2, 2, we get 0. They're solutions, yes? What's my orthonormal eigenbasis for A? Beta. Almost done, right? All we got to do, normalize these things, right? So I got 1 over root 2, 1, 1, and 1 over root 2 times 1 minus 1. And if we calculate beta transpose A beta, we work that out. What we're going to get is simply 3, 0, 0, minus 1. And you can check that that basis matrix that I'm talking about, right? Beta, it's, 1 over root 2, 1 over root 2, 1 over root 2, minus 1 over 2. You try it out. That matrix, the inverse is the transpose. The determinant's minus 1. So when you flip the diagonals and you multiply by minus 1, it puts them back where they were. And when you put minuses on the off diagonal, and then you multiply by 1 over the determinant, it puts the diagonals back where they are. So like, you can check. The transpose of that matrix is in fact its inverse. And that is the orthonormal diagonalization of this matrix. That was inescapable by the real spectral theorem. As soon as this is symmetric, I know this has to happen. There has to be an orthonormal eigenbasis, which isn't to say that every eigenbasis is orthonormal. It's just to say that there exists an orthonormal eigenbasis. So like next class, I'll try to show you an example where we have more than one, like the eigenspace is two-dimensional. And when you have the eigenspace be two-dimensional, you could find a basis for eigenvectors which is not perpendicular, and so it wouldn't be orthonormal. But in that context, the real spectral theorem says that if you Graham-Schmidt the basis, you can put it into an orthonormal form and not spoil the eigenspace. Anyway, we'll see that next class. But yeah. Oh, application. What if I wanted to calculate? So the other thing I asked you guys in surprise attack mission. So here's a big hint. I asked you to calculate a to the power n. We talked about this before, but just to remind you, how would you calculate a to the power n? I suggest that you calculate, well, in this current context, beta d to the power n beta transpose, right? We worked this out before, like if you multiply, we have the formula A is equal to beta d beta transpose. And so like A squared beta d beta transpose beta, man, this is awful notation, d beta transpose. So that ends up, these guys cancel and you get the d squared in the middle. But calculating the nth power of the diagonal matrix is what? 3 to the n minus 1 to the n, right? So one of the problems in your surprise attack mission is to calculate the nth power of a matrix. The way to do that is to use diagonalization like I'm talking about here. So just a quick hint. I shut up. See you guys Thursday, I suppose.